Thank you. I will begin with a word of prayer. Heavenly Father, we thank you again for this day. I thank you for the break just completed. Just pray that you help us to make the most of this short time we have together today, Lord. In your name I pray. Amen. Okay, so wanted to try to prove as much as I could of Theorem 2.21 today, and maybe talk a little bit about the structure there. So, of course, we're, as usual, in Brian C. Hall's Lie groups, the algebras, representations, and elementary introduction. And so Theorem 2.21 says the following. You have G and H matrix Lie groups with the algebras frac G and frac H. Give it some feet there. Respective. Suppose you have capital Phi, which is a mapping from G to H. What kind of mapping? A Lie group homomorphism. What's a Lie group homomorphism, guys?
Preserves the group operations and it's continuous.
It should preserve the structure of a Lie group, right? So it might suffice to say it's continuous, but I'm more comfortable to say it's smooth. So there's probably some way of capturing it in terms of a limit or something, since we seem to be shying away a little bit from the manifold structure here in places. But anyway, then there exists a unique R-linear map Phi from frac G to frac H such that Phi of the exponential of x is equal to E of Phi of x, little phi, for all x in the Lie algebra G. All right, and we also have these three fun facts. One, little phi of A x A inverse is equal to big phi of A little phi of x big phi of A quantity inverse. And that's for all x and G at A and big G, for all x in frac G. And so, in other words, for all x in the Lie algebra and all A in the Lie group. And then a second fun fact, the little phi of the commutator of x and y is the commutator of phi of x and phi of y. And that's for all x and y in frac G. And 3, phi of x is equal to dpt of capital Phi of e to the tx. You take that derivative and then at the end of it set t equals to 0. Now, I think in my previous mathematical existence, as far as I remember, this is not the notation I've thought about this theorem in. So, like, come on. I'll eventually figure out how to keep this book open. I need to return that screwdriver to Dr. Wang. Well, gotta get to it. I still need to fix this stupid whiteboard. I haven't gotten to it yet. As I mentioned to you, I got sick, and I always get sick over break. It's inevitable. All right, so let's see here. Let me try to recast this in terms of. I personally like to think about. Just think about it like this. Okay, so here's the Lie group G. Over here, here's the Lie group H. I think of them as like curved spaces inside GLN, right? They're manifolds. They're something like, they could be like, think of them as a sphere or a torus inside, whatever you want to kind of use as your mental picture for it. And then there's this homomorphism that goes from here to here, right? This phi, right? So phi being a homomorphism, it'll map the identity, let's say 1 in G, over to the identity, which is 1 in H, right? So like phi of 1 in G will be equal to the 1 in H, whatever that is, or maybe we're using E, I forget. Right? It maps the identity to the identity. Since it's a homomorphism, that's part of what it means for it to be a group homomorphism.
And that's big phi.
The big phi. Oh yes, thank you. Sorry. And then the claim is that there's a little phi which maps frac G to frac H. Well, as I've explained to you guys before, we can also view the Lie algebra, right? We can view the Lie algebra as the tangent space to the identity at G. So like the tangent space to the identity here, the tangent space to, let's say, the identity of G is also identified with frac G. In particular, what did we have, like, remember we had like the mapping, something like gamma of t is equal to e to the tx. That gives us this one parameter subgroup. The exponentiation of x in the Lie algebra gives you this one parameter group and the subgroup of the Lie group. And so all such x form the Lie algebra. But another way of looking at that is the tangent vectors, because if you differentiate this and plug in times 0, you get back x. So like gamma prime of 0 is x, right? And so x is a typical tangent vector in here, right? And so, well, as we talked about in advanced calculus, if you have two manifolds, you can look at the differential of a mapping, right? And that will map tangent vectors at a point, what, at the 1, at the identity in G. It'll map it over here to, what does it do? Well, d phi 1 in G is a mapping from tangent space at the identity in G of G to the tangent space at phi of the identity, right? In H, but that's exactly the tangent space at the identity in H to H, right? So the differential of a Lie group homomorphism, right, is naturally, or if you like, we call it the push forward at a point. It's naturally a mapping from the tangent space to the identity at G to the tangent space to the identity at H over here, right? And since these are, we can both think of these as subgroups of GLNC for some n if you want. I mean, I guess there's not too much harm in that. I guess it could have different n. Fine, I guess these could be like 4x4 matrices, and these could be like 7x7 or something stupid. So I shouldn't assume they're the same size. And this could be a different identity here and here, you know. Fine. But the point is the differential of a Lie group homomorphism gives us a natural mapping. It at least goes from the Lie algebra of G to the Lie algebra of H. I think that's already clear from just basic manifold theory, like the construction of the differential. So there you go. I mean, that's, for me, that's existence. That, I mean, there exists. I would say that phi is equal to, what's phi equal to? I'm pretty sure I can claim that phi is exactly the differential at the identity of big phi.
What does a number? How does it relate to number 3?
Yeah, that doesn't get us 1, 2, or 3 yet. But
Okay.
right. And in fact, I'm not entirely sure. Let's see, what can we even get? How about this part? So would
Phi
phi,
is the differential.
yeah, phi, capital Phi of e to the x, is this equal to e to the differential? You see, differential of phi, right? Acting on x, right? What does that even mean?
E to the x.
See, if I was to just full board, like physics style, try to calculate this, what I would do would probably be my next step to try to understand what this is, would just be interpreted as a power series. This would be like the identity plus the differential phi plus 1/2 the differential of phi squared plus da 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 da, you know, acting on x, right? Which would be like I acting on x plus d phi acting on x plus 1/2 d phi of d phi acting on x. You know, like that. And let's see here. Yeah, it's not at all obvious to me how to see that identity in this way of thinking.
What is capital Phi though?
Capital Phi is a Lie group homomorphism, and all we know about it is that it preserves products and it's smooth. So like we know, we know like phi of AB is equal to, maybe I should say G1, G2. Is phi of G1, phi of G2, like that. So no, in terms of interpretation there, I'd have to think harder about how to find my way to proving what I underlined in purple over here. There is definitely an advantage to taking the notational stance, which Hall has taken in his book, because as I read these earlier, I understood them. I mean, so this is part of the sneakiness of his approach, is it makes some of these things which would otherwise be rather technical, hard to see things from from just like a straight, if you just kind of take the straight road in manifold theory, I think some of these things are harder to kind of wrap your mind around because of how you're tempted to try to calculate it, like I'm doing right here. Right? Now, like for this, for example, what's he do? He's like, okay, so well, maybe he doesn't get to that just yet. I don't remember, but let's follow his proof. Well, he's like, first of all, what does he say? He says phi of e to the tx. What is this? This will be a one-parameter subgroup of H, right? Does that make sense to you guys? any choice of x in the algebra. Now, that should make sense to you because, okay, so if I take a curve here, right, like that would be a point on here would be something like e to the tx, right? And so that will get transferred over to here, basically. And that would be like phi of e to the tx. You can check it. Phi of t equals to 0 gives you the identity. And you can check that it has the one parameter group property, like phi of t times phi of s is equal to phi of t plus s. I should say gamma or something. We're using phi in a different context, but
That's true because the exponential.
right, yeah. And we proved that before. So it's a combination of like, no, if I do this, let me just write it out. It is a combination of the exponential, which we worked out before, right? So here would be, so if I call this thing, say, gamma, so here's like gamma of t, gamma of s, which would be this times that. But then by the group homomorphism property, that's v of what? Right. But then because the exponential also gives you one parameter group in G, this is right, which is, by the way, gamma of t plus s. So that's part of what we need for it to be a one parameter. Ooh. Put that there. One parameter subgroup, all right? So, okay, well that's great. Now that you have that, he's like, well, that means then, right, that phi of e to the tx, what do we have, the harder thing, right, is that any one parameter subgroup is given by the exponentiation of something in the Lie algebra. In this case, the Lie algebra of h. So this has to itself be equal to e to the tz for some, what? For some z in frac h. Because it's a one parameter subgroup in h, so it has to be met by the exponential of some h algebra element. Now, so then what? He says, so, okay, so what's his definition of little phi? He says define little phi of x equal to what? His definition is just totally hands off.
Since we want it to be little z.
Z, right. Okay. I guess. Fine.
It's got to show it's linear. It has those properties.
I'm just, I want to go back to how is this, right? Contrasted with my intuition, which is that it should be that phi of x is equal to what? di big phi, right?
It's 3 o'clock p.m.
Of x. You see the difference? Look at his way of defining things. There is no explicit appearance of the Lie group homomorphism in his definition. Totally wrapped up in here, in that. Man. I'm tempted. I shouldn't. Tempted though. I should. Oh, whatever. I'm gonna do it. You might be tempted to solve this. How would you guys solve for z? If you were so foolish as to try such a thing. solve this for z, how would you do it?
Take the log.
How about, yeah, phi of x, right? Phi of e to the x is equal to e to the z. Like you said, take the log. The log of phi of e to the x, right, is equal to z then. So let's see here, in other words, little phi of x is equal to this, right?
Is this for t equals 1, or?
Yeah, I just set t equal to 1.
Oh.
It's kind of fun. I'm just being informal here for just a second. Can we just humor me for a second here? Can we derive any of these with that formula? Like really pretend you're a physicist for a second here. Throw domains and applicability of formulas. Caution, throw that thing to the wind. Ignore sorts of cautions and mathematical encumbrances with which we live our life. Phi of ax a inverse. So would you have like? Is there any hope for that?
Isn't there like a property of the matrix log that says something like that?
So we'd have phi. Yeah, I don't know. E to the. Well, I guess we do have.
So you can take the a's out of the exponential.
Right. But then this is a group homomorphism. By the way, the image of the inverse is the inverse of the image. So it doesn't matter if I put the inverse inside or outside there. Well,
Well, you can turn the phi of e to the x into e to the little phi of x.
right.
And then put the phi of a's back into the exponential.
You have phi, what did you say, a?
Yeah. Yeah.
A, and then little phi of x?
No, then times e to the little phi of x.
Oh, right, I'm sorry, that's what I was trying to. So just do like that?
Well, no, it's phi of a.
I'll keep the phi of a
Yeah.
and the phi of a inverse, okay.
Right, and then we put those back into the exponential.
Ah, right. So it's always using this exponential, I don't know what you want to call that identity, like unfolding or something.
Well, you won't have the phi of a's.
Oh, yes, I'm sorry. Thank you.
Right, and then the log cancels with the exponential.
Of course. Actually, I mean, no joke. Like, cool. Hey. You didn't have to look at your book this time, but I would suspect the proof we'll find it here is a little bit more rigorous. I mean, he does make many of the same steps we just made if you read ahead in the next page. Let's see here. The first thing, so this, the purple thing from his definition is immediate.
Yeah.
Just put t equals to 1, right? Do you guys see that? To get this, you just take his definition and put t equals to 1. Over here, t equals to 1. Big phi of e to the x is e to the
Oh, yeah.
z, but z is phi, little phi of x, so there's that. Step 2 he's like, step 2 on page 46, little phi of Sx is S times little phi of x. He said that's also immediate, again, because of the property of the exponential, essentially. I mean,
So, do we know this this phi is unique already, or do we have to prove it?
yeah, uniqueness comes from that difficult thing we didn't actually prove the other day. There's a unique z for each one parameter subgroup through the identity. You pick a one parameter subgroup through the identity, there is a specific Lie algebra element which exponentiates to that one parameter subgroup.
You may just not remember.
That is where the uniqueness comes from. That was the thing that I was getting hopeful I could prove, but then reality set in that it was rather technical. I think that's, where was that? Oh, where was that? Well, surely it's in this chapter. I'm just not seeing it. It's right in front of me. I'm just not seeing it. Oh, it's the page 37 to 38. Page 37 to 38. That's where it's proved. It's somewhat involved. So, Theorem 2.13 in particular. If A is a one-parameter subgroup of GLNC, then there exists a unique n by n complex matrix X such that A of t is equal to e to the tx. So Theorem 2.13 gives us the uniqueness I'm claiming. All right, so excuse me. So that's kind of fun. We figured out our own little proof here. Now, I think the shortcoming of our proof, of course, is what? What's the domain of the logarithm, right? So we can't take the log of just any matrix. That may be somewhat limited. Our argument may only hold in a special case, whereas if we study the totality of his argument, we may get more a large, wider applicability to the argument, right? All right, I'm going to talk more about that argument next time, probably. Let me just stop and smell the roses here before we step away from this. I just want to point out to you really what this says. All right, so this says that some sort of conjugation, right, so this is a conjugation of the algebra by the group. So you're taking algebra elements and you're multiplying by the group and the group inverse on both sides. So it's kind of like an external conjugation. Because you're not conjugating by something in the algebra, you're conjugating by the group. So this is some sort of like group action on the Lie algebra. And what this says is that this homomorphism, that there's a natural preservation of the group action under this homomorphism and the corresponding Lie algebra homomorphism. By the way, this is what this says. It says that the bracket in G is preserved to the corresponding bracket in H. This is precisely the statement that the little phi is a Lie algebra homomorphism because it's a linear transformation which preserves brackets. Lie brackets, that's what's called a Lie algebra homomorphism, preserves the structure of Lie algebras. And this here, I don't have a quick interpretation of that. This is probably, actually when you get right down to it, this 3, honest to goodness, is saying this. These are the same statement, just in different formalisms. That's what's going on there. So just to boil this theorem down to its core, what it's saying is for every Lie group homomorphism, you get a corresponding Lie group Lie algebra homomorphism. So there, and this story, this interweaving of the group and the algebra continues throughout the study of Lie groups and the algebras, which is part of what makes it so much fun to look at. Is like every interesting theorem you get for groups, there's a corresponding theorem for algebras, and sometimes they look quite different. And both Lie algebras and Lie groups are important to physics and lots of other things. Like, I mean, they're everywhere in manifold theory and in applications. There's like Lie groups all over the place. Because it's just algebra and calculus, you know, if you've got both happening, you've probably got Lie algebras and Lie groups. Well, playtime is over. I mean, playtime has begun. So I'll see you guys. Again, we'll have to make up for this at some point, but